Hello AP Chemistry and welcome to Chapter 7. This video is probably going to cover 7.1 and 7.2 because 7.1 doesn't really have a whole lot in it. It just talks a little bit about the development of the periodic table, which we talked about last year. We credit the periodic table to, Dmitry Mendeleev, He gets credit for the periodic table, though there were actually several scientists that were, there were lots coming up with an order for the elements that we knew at the time. And there was at least one other scientist that had the exact same organization. Just Mendeleev was a little bit more vocal about his. If we take a look, just basic historical things we should know, If we look here, this is just a chart of the relative times we found elements, So some of these elements, iron, copper, silver, gold, mercury, tin, lead, carbon, and sulfur have been known since ancient times. As long as man has been walking the earth, we have record of these elements having been around and people having used these. Now, what makes those elements different and unique from the rest of them? Ding, 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 Those are ones that we mine from the earth in their natural state, We find those in nature present as they are, Whereas a lot of these are present in compounds, stuck to something else, or these, which came relatively late. Why do you think these came so late? There's no way to grab them. There's no way to find them. If they are gaseous and we cannot see them and they don't react with anything, they're going to be hard to find, So anyway, and then obviously these are some of the very most recent, And these are ones that we've currently discovered, which really means created, courtesy of particle accelerators. Couple of things to note, In terms of history, you'll see that there are a lot of blue ones, Blue and yellow, so if we go through here, around the 1800s is when chemistry was really born and came into its own as a science, Which is why this is where we get the boatload of our elements from. Okay, going back to the periodic table, When Mendeleev came up with his original model for the periodic table, he had silicon, but germanium was absent. Nobody had discovered germanium yet. Now, when he designed his periodic table, he left a blank spot here for germanium. And he predicted that it was going to have an atomic weight of 72. He predicted its density, its specific heat, blah, blah, blah. He predicted all those things based on periodic law, Based on the fact that where this is in a group and where this is in a period, he could predict all those properties simply based on its location, because all of that goes back to what is it composed of in terms of protons and electrons and how those things are arranged, And that's really what this chapter is about. It's about taking those periodic, those electron arrangements we talked about previously, and how do we use that to come up with a whole boatload of properties simply based on location and what is essentially their arrangement of electrons. So, that brings us to effective nuclear charge, which explains half of the properties we're going to talk about. So, Coulomb's law, which we referenced back in chapter 4, says that the force of an electrostatic attraction is equal to K, which is a constant, Q1, Q2, over distance squared, Where, when we're labeling these, this is a constant that you don't really have to memorize because we're not really going to do math with this so much as a qualitative analysis, This is the charge of one of my species. This is charge of the other species. This is the distance between my charges. And this is the force of attraction or repulsion between any electrostatic species, Where when we say electrostatic, we just mean charged species, So if we say electrostatic attraction, we're talking about the attraction between charged particles, or repulsion if that's what it happens to be. Now, if we think a little bit about this, we're aware, that ideally we're going to have opposite charges, So we'll have something with a positive charge, something with a negative charge, which means my overall force is going to be, negative. Meaning, again, energy is released, like we talked about previously, and a release in energy, Anytime we go down in energy, that is a favorable thing, We become more stable if we release energy and come down, Obviously, if these were both the same charge, this would be a positive, Which means we'd be talking about repulsion, and this would be the energy of repulsion, or the force of repulsion between my two particles, Coulomb's law, super duper important. If we look at what this essentially says, this says as my charges increase, then my force of attraction increases, right? The distance between my particles does what? Right, as my distance decreases, my force of attraction also increases, right? So we want charges that are high and close together, and that gives us the strongest force of attraction. Okay, let's talk a little bit about nuclear charge, right? Because obviously, if we're talking about Coulomb's law, we're going to be talking about charged particles. In this case, we're talking about my nucleus. So here we're talking about sodium. Sodium contains 11 protons, right? Which means that the Z is 11 for sodium, okay? Now, Z effective, the effective nuclear charge, right? Z is nuclear charge, effective nuclear charge. And when we put the word effective in front of something, we mean, right, the amount that is actually doing something, okay? So this is one of the ways that we talk about how much attraction a valence electron will feel, okay? Z effective is how much attraction my valence electrons will actually feel to the nucleus. Now, bearing in mind that the valence is always going to be our outermost shell, that means we're going to have core electrons on the inside, right? Which means basically this is outside, then we have all these ones on the inside. So if we look here, sodium has a total of 11 protons. A neutral sodium atom would have 11 electrons. We'd have this one out here, if we think about sodium's electron configuration, right? It would look like neon 3s1. Okay, so then what that means is we have 10 electrons on the inside and 1 on the outside. And so that's what this picture is showing, right? There are 10 core electrons, and they screen or shield, that would also be okay, they screen or shield the valence electrons, as in these, since they're closer in proximity, are going to feel more of the attraction of the nucleus, right? And this is going to get whatever's left over. So what this equation says approximately, and this is a really rough approximation, right, is that my effective nuclear charge is approximately equal to my number of protons minus whatever my number of core electrons is. So in this case, we have 10 core electrons, right, which means that my Z effective is approximately 1, right, meaning that this electron out here feels approximately the pull of 1 proton, all right? Okay. Orbital shape affects your Z effective. So this, again, right, this is an approximation, okay? And there are some variances that have to do with shape. So thinking back to chapter 6, we said that an s orbital relative to a p orbital penetrates closer to the nucleus, okay? The s orbital penetrates closer to the nucleus than an s orbital does, right? And if we're looking here at this diagram, right, we can see that quite clearly, right? Here, again, distance from the nucleus, electron density. This one says that we have a small peak right here, which gives us a little bit more close to the nucleus than this one does, right? So what that means in terms of shielding, right, is that even though if this were my valence, if my valence were 2, this s electron, since it's closer to the nucleus, is going to have a higher Z effective than my p electrons, okay? In this same shell, note that these are the same shell. In the same shell, my s electrons are going to have a higher Z effective than my p electrons, simply because the s ones are able to be closer to the nucleus at some points in time. Okay? All right. Now, looking at this from a different point of view, right? Here we have this beautiful graph with all kinds of information on it. The important parts are going to be this one, and we'll talk about this one. So, this black line is the charge of my nucleus. So they will see here's lithium, beryllium, carbon, fluorine, neon, sodium, blah, 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 right? So here we have what is basically period 2, and we have period 3. Okay, and so what's that black line represent? Right, this black line represents my actual number of protons. Okay, now Z effective for my core 1s electrons. What do we know about 1s electrons relative to any other electrons in an atom? Right, those are the ones that are closest to the nucleus at any given point in time and closer than any other electrons are going to be. And so we'll see here, right, that the Z effective for those 1s electrons is essentially equal to the charge of the nucleus, right? Because they are adjacent to the nucleus, they feel the complete pull of the nucleus, so they get their Z effective is Z, okay? Now, when we get to our valence electrons, so our valence electrons are the ones that are in the outermost shell, right? So for these, it's shell 2, and for these, it's going to be shell 3, right? We see that it's going to be lower, right? And if we think back to what we talked about, lithium, for example, has, if we look here, right, has 3 protons and 3 valence electrons. Now, if there are 3 valence electrons, there are 2 core electrons, which means that over here, Z effective is approximately 1, right? And which means that that 1 valence electron feels the pull of approximately 1 proton, okay? Beryllium has 4 protons, 4 total electrons, 2 valence electrons. Those 2 valence electrons approximately feel the pull of 2 protons, have a Z effective of 2, okay? Boron, right, has 5. They feel a Z effective of 3, right? So this trend continues, right? And we'll see that Z effective, right, actually increases across the period, okay? Z effective increases as we go across a period. Even here we'll see that for period 3, Z effective increases as we go across a period. Okay? Huge drop between neon and sodium. Why? Right. So if we look here, right, what happens as we go from neon to sodium is we add a shell, right? By adding a shell, what that means is that all of these now become core electrons, okay? Which means that now these are being shielded by those 1s electrons and 2s and 2p electrons, right? So there's an increased shielding, right, as we move to period 3 because, right, again, now we have our first shell and our second shell shielding our third shell from the pull of the nucleus, which is why we get a sudden decrease in our Z effective, right? And then again, as we go across the period, it's going to work its way up again, slowly but surely. Yes? Makes sense? All right. Fantastic. Hang on. I forgot to put my little yellow marks down here. Tell me when I was actually done or not. Yes. Yes, we're done. Okay. Thank you for listening. Be good, and I'll see you soon. Bye.